Okay, hi everybody. My name's Allan Cantle, and I'm president and founder of Nallatech. We specialize in data-centric computing, specifically using FPGA technology. And today, basically, I want to talk about, it's really a 101 guide. This may seem a little bit odd to some people, but heterogeneous or accelerated data-centric computing. We've been talking about that all day. I sort of feel that there's a lot of acronyms going on. We hear many of these acronyms, and I'm sure all of us understand some of them to a greater or lesser degree. But what do they all mean in what context, and what's really going on here? So I want to really give a story of where we've been in the world of computing and where we're going. And I think really, if you look at the computers of today, they still pretty much look like they did 10 years ago. But we're all talking data-centric, and I think OpenPOWER is taking us to a much more data-centric world, and that's what I would like to articulate today. So, right back in the history, processor-centric evolution. We've lived in a processor-centric world for well over 30 years, and it has really been a laser focus on increasing ops and flops, and that's been the main driver. And the data has really played second-class citizen. But way back in 1977, John Backus coined the von Neumann bottleneck of getting data to and from the CPU. I won't read that paragraph out there, but if you look at it later, it's very applicable to today, uncannily, actually, when I read it. So Intel, way back in 1985, with their 386, introduced external cache memory for the first time on the x86 architecture. And really, ever since then, as the clock speed of the processors been getting faster and faster, the relative distance of the data has been getting further and further away, exacerbating the problem. But sure, we've had a fix for that year after year after year, increasing levels of cache, exotic local disk caches, operating system tricks, and virtualization overhead has been coming around and making multiple copies of this memory. So this is all well and good, but really 30 years of this same solution of fighting this von Neumann bottleneck has really become a crutch that we entirely rely on as an industry today. And we can't break this crutch without breaking the entire system. So it's not something we can throw away. So just take a look at it in another sense. This is an abstract view of the CPU at the heart of the world with all of its layers of memory around it. At the far right-hand side, you've got your NAS, your big storage engine. And if we take a look at the path of our data, typically today, it comes through the NIC, through the PCI interface, and gets copied into the multiple levels of cache, gets copied back out to memory, and maybe into disk storage. What happened there? OK, so just taking a look at, I'll repeat myself here, just taking a look at a millisecond in the life of your data, starting out in your network-attached storage. Basically, it travels in through the NIC, through the PCI interface, gets copied into the multiple levels of cache and actually your memory, and potentially additional disk caches, et cetera, or local disks. So there's much copying going on here, all in the name of coherency. And really, in reality, the CPU is really efficient when it's working out of level 1 cache. You can't beat it. But it's very distant from its primary data store. That's the bottom line of where we've ended up at today. So just going back to this slide, the processor-centric legacy we live in. So we've got memory copying and data movement is going on all the time, and that's really where the most power gets burnt in a system. Again, just reiterating, CPU and level 1 cache is very low power, and non-volatile data is actually 0 power. So all of the power in our computing systems is spent in moving this data to and from the processor. And this is a well-understood problem. So really back maybe 10 years ago or more, Google were probably the first to really take a look at data-centric computing because they had a big data problem, obviously, with the internet, et cetera, and the search. And they put the focus on this. But they played with the system-level components in terms of trying to make the processor a bit closer to the data. They restructured. We all know what they've done with MapReduce over the years now. And that was the beginnings of trying to make these CPU-centric architectures more friendly to data-centric applications. Additionally, what happened was some of these buzzwords and acronyms you hear read many times over, RDMA, DPDK, IWARP, all of these techniques are ways of trying to circumvent their circumvention strategies over a lot of this copying, trying to improve performance and minimize power or any unnecessary copying, as also was talked about by John earlier. So really, essentially today, we're still living in a processor-centric world that is being adapted for data-centric applications without completely breaking the traditional programming model for good reason. We can't really break the existing programming model. So what about the accelerator side of it? So that was mainly the data movement, but on the accelerator side, we all know now that the GPU is a king of acceleration, and the FPGA is now getting a lot more adoption, as you've probably seen today. GPUs are really traditional flop amplification historically, and FPGAs are the archetypal data-centric deep pipeline computing is where they really come into their own. But really, at the end of the day, we're increasing ops and flops or keeping the data more local to the CPU, these subtly different architectures. But if we look at our path of data again, from a CPU's memory, the traditional path is it would actually get copied to and fro the memory before it got passed to the accelerator. Or if one accelerator wanted to talk to the other accelerator, it would have to go through the system memory twice and before getting to the accelerator. So when in reality peer-to-peer has been supported in PCI forever, it never really got utilized in a CPU-centric architecture. But today, you can have the peer-to-peer, and NVIDIA have coined that GPU direct, in moving data directly between accelerators. So really, we're beginning to become more like peer processors. Really, the lines are becoming blurred between these different devices. FPGAs are adding processors. GPUs are they're becoming more processor-like in their cores. Processors, the main CPUs are adding GPU capability. And in reality, even more so today, as processors are pulling FPGAs on board, GPUs are introducing more streaming-like functionality, copying the FPGAs. And even FPGAs from Xilinx, for instance, their next generation will have some GPU content in it. So the lines are certainly blurring, and these are becoming peer processors more than host and accelerator. And really, this was understood back in 1998 by our friends at DARPA, and they coined the phrase polymorphic processor. That was a processor that was good at all these different abstract data types. And it looks like we're really on a journey of invention towards this polymorphic processor now. So OpenPOWER, what's this all about? It's data-centric. Really, the OpenPOWER Foundation is taking data-centric to the next level through collaboration. IBM opened the power architecture at the chip level. So they're enabling really collaboration around polymorphic processor innovation is what we're actually seeing there. And the OpenPOWER architecture has been opened up at the system level, enabling data-centric system architecture innovation and really changing the game on how processors, accelerators, memory storage, and networking interact with each other. And certainly for Nallatech, and I'm sure for some colleagues out in the audience, they're allowing data-centric computing experts like Nallatech, we've been doing this for over 20 years, data-centric computing, to have a voice and actually be heard and contribute to this community. So a little bit about Nallatech. We focus on FPGA accelerators. We were the first CAPI-enabled accelerator back last year, a couple of years ago, with a network-attached acceleration that was good for compression, encryption, financial services, as you've heard some presentations today, and intrusion detection, et cetera. And we have compute acceleration at the other end in this. This is a GPU form factor, a card with dual FPGAs in high memory bandwidth, good for oil and gas migration algorithms, machine learning, video encoding, and bioinformatics, as a couple of examples. And today, I'd like to announce, if you've seen, may have seen on the show floor already, we've now completed the set of inline acceleration, so to speak, with our storage accelerator, which is CAPI-enabled in collaboration with IBM, which is a single Xilinx FPGA with 2 terabytes of NVMe flash attached to that FPGA. This is great for in-memory database applications, inline compression, and in-store and algorithm acceleration. Lots of different acceleration ideas to come. Additionally, in Europe, Nallatech is the EU government has funded some exascale research programs and data-centric computing programs, and Nallatech is the key partner in that consortium with IBM and Hewlett-Packard Enterprise, and we have a CAPI flash card. Sorry, I beg your pardon. A CAPI network attached card for actually bringing CAPI to non-CAPI to non-power architectures. So this is an IBM Power 8 box being coupled to a Moonshot, a box from HP with our CAPI accelerator technology. And we're exploring some different algorithms with that consortium over the next couple of years. So I'd just like to leave you with a little bit of a data-centric architecture prediction, and maybe you guys can help us make this happen. DOE's big target number is less than 20 megawatts for an exascale computer. And you know, we're working our way towards that, but there may be a long way to go. But I think this is a destination that we're all working to. When you look at this from a data-centric perspective, we've got our polymorphic processor. We've managed to innovate our way to this new processor. But we have 3 flavors. We have a relatively small processor that's storage attached, medium-sized processor that's DRAM attached, and just a raw compute processor, maybe with no direct memory except for maybe level 1 cache buried in it. And that will have a control plane that's very traditional to our networks today, but that's going to be classed as really a low bandwidth, fabric switched, managed, and it's going to be managed coherency rather than default everything coherent control plane, and that will be a classic switched electrical network that we know today, fabric switched. But we'll have a data plane that is 0 power and very high bandwidth, and it's optically enabled to get to the 0 power. It's absolutely non-coherent, so we don't have all this copying going on, but it's for a streaming data plane, for moving data between these different nodes. And you basically compute in a distributed fashion where the data is. When you think you've got an exabyte of data, you don't want to move that anywhere. You'd rather have an idle processor that maybe gets used once a year than moving terabytes of data. I'll leave you with one little thought there. If you look at the processor image, to make a processor on an FPGA needs a 20 megabyte or 30 megabyte bit stream. Wouldn't you rather move 30 megabytes of data around than 2 terabytes of data around? So we need to start moving the processor closer to the data, and this is one idea. Anybody that, you know, any funders out there that can help make this happen, but OpenPOWER as a community, we're all working together, and I think this is the ultimate destination. Just my own idea there. Thank you.